Okay, this is a quick sample uncertainty calculation video. The goal is just to kind of run you through how to do this. So let's say that you have a rectangle and you measure the length and the height of that rectangle to be those numbers. And the first thing we have to talk about is, where did those numbers come from? What do they even mean? Well, you probably measured them with a meter stick, for example. And on a meter stick, these divisions are centimeters, and these smaller divisions are millimeters or tenths of centimeters. Well, generally, the procedure is this: you line up one side as best you can with one of the divisions, so that's lined up with the 7, and then you get as far over to this side as you can and you decide where it lines up. For me, this is 50, this is 51, this is 50.5, and you might just stop there and call it a day. But you might also say, wait a minute, how close to the line does it lie? Can I guess? Can I estimate another digit? Is it halfway between these two, or is it right on the line? Now, in this particular case, this guy looks right on the line to me, and so I call it 3.50. And you might say, how could you possibly know that it's directly on the line? Maybe it's 0.9, maybe it's 0.8. It's okay. What I'm going to do is give myself an uncertainty of half of the smallest division. The smallest division is 1 millimeter. And so I give myself half of the smallest division. There are people, reasonable people, who may disagree with this, but no one would say that this is crazy. This is a sort of rule of thumb, half the smallest division. And what this means is that since I'm allowing myself such a generous uncertainty, I'm allowed to guess. So it happened to fall right on the line, but if it fell halfway in between, I might guess an extra digit, which is what I did for the height. I'm not going to show you the height, but you can imagine that the height landed maybe a little to the right of one of the tick marks. And I said, well, it's not halfway, it's not 3/4 of the way. I'll just call it 0.2 and give myself a generous uncertainty. What that means is that these numbers that I reported are actually incomplete. I need to include my uncertainty with each of these numbers. And notice that my uncertainty goes to the hundredths place, and my measurements go to the hundredths place, meaning I have some uncertainty about this digit, but I have very little uncertainty. I have less uncertainty about that digit. Okay, so what does this say? This could be 2.47 to 2.57. Okay, so that gives the person I'm giving this information to an idea of the range of values I'm giving. Every measurement is a range. The most precise measurements in the world are a range. Okay, so those are the measurements. What if I want to do something with those measurements? Like, what if I want to calculate the perimeter? And it's pretty easy to calculate a perimeter. It's twice the length times twice the width. If we crunch the numbers, there's my 12.04. I didn't do anything special there. I just added the numbers. Now, you may have had courses before where you talk about sig figs and what the rules are for calculations in sig figs. I'm going to kindly suggest that you throw those in the garbage. These are all about implied uncertainty. And what we're going to do is be in uncertainty. We are going to be explicit about our uncertainty. In other words, this is just a placeholder. Don't worry about how many digits it has. I'm going to fix it later. So how do we fix it? We need to find the uncertainty in the perimeter. And the uncertainty in the perimeter is given by the sum of the uncertainties in the thing that make up the perimeter. Now notice this less than or equal to. That means that the uncertainty in the perimeter is less than this. This is provisional rule number 1. It's in the lab manual, and it says that the uncertainty, the instrumental uncertainty that we're quoting in the perimeter, should be less than that. We will get a better rule later that will actually give us a way to calculate a number that's less than that. But for now, let's be overly generous with our uncertainty so that we can understand how to calculate with these numbers. If I do this calculation, it's pretty straightforward. I get 0.2 centimeters. In other words, my uncertainty in the perimeter is 0.2 centimeters. If my uncertainty in the perimeter is 0.2 centimeters, this is garbage. It means my uncertainty is somewhere between 11.84 and 12.24. Is this number wrong? No, it's not that it's wrong. It's just that it's not particularly helpful in such a large range. That number has very little value. And so this is the rule. The rule is you don't worry about sig figs. You first find what decimal place what decimal place your uncertainty is, and then you match your measurement to your uncertainty. That is how you report the measurement. You cannot know how to report the measurement until you have calculated the uncertainty and then you match the decimal places. Okay, so much for that. That's the perimeter. What if instead we wanted to find the area? Okay, well, I'm going to do the exact same thing. The area is length times height. I multiply these numbers. I get this number. Again, it's a placeholder. I don't care about sig figs. I will figure out exactly how many digits to include later. How do we find uncertainty in area? Well, in this case, the area is a product. It's one thing times another. And so we go to provisional rule number 2, which is for products and quotients, the uncertainty, the fractional uncertainty, in other words, the actual uncertainty divided by how big the thing is, the percent of how unsure you are, you find that it is less than adding the fractional uncertainties of the things that go into it. Okay, so here we're multiplying, but it's also true if we were dividing or squaring or any of those other things, we would use that same rule. So if I multiply all this out, I do that, and on my calculator, I'll tell you, I get this crazy weird number. I get that crazy weird number. And also, the other issue is, at the end of the day, I don't particularly care what delta A over A is. I just want to tell someone what the area is. So how do I find just delta A? Well, delta A is delta A over A times A. In other words, just multiply it by A. What's A? It's 8.82. If I multiply 8.82 times this number on my calculator without getting rid of any digits yet, I get this number. Okay? Our rule is that we keep one sig fig. One sig fig. So if you like sig figs, here's your chance to shine. You get to keep one sig fig in the uncertainty. Why? Is it wrong to keep more? No, it's just not particularly helpful. All of these rules are here so that your measurements may be helpful to the person who paid you for them. So if we keep one sig fig there, our uncertainty is 0.3. And what we do is we report this measurement to the tenths place only. I have tenths in my uncertainty, and so I only report tenths. I rounded to tenths in the reported area. So if you had this rectangle and somebody paid you to find the area and perimeter of it, you would, in order to earn your paycheck, report these things. Notice that the uncertainty decimal place matches the reported measurement decimal place. We'll come up with better rules later on to narrow down this uncertainty a little bit, but if you understand this process, adapting to those new rules will be a piece of cake. Okay, hopefully this video was more helpful than confusing.